Thanks for all sticking around late in the day. I know we're all tired, I am too. But this is a continuation of yesterday's talk. Yesterday I kind of gave you an overview of what the problems are in the solar system, what questions we have, what we know. Today I want to go over a bit more of how we know it. And so in particular, where a lot of these physical properties I was talking about, this dichotomy between rocky and icy bodies comes from, how we know these things we think we know about the solar system and its history. And to go into this, we have to start with how we discover asteroids. And when you first discover an asteroid, it starts out as just a dot moving against the background sky. And so this is a series of images taken from the Gemini South Telescope in Chile of, in this case, asteroid 2014 VG60. This was a near-Earth object that was originally discovered by the WISE mission and required follow-up in order to confirm the orbit. And so these data were used to help confirm the orbit of this near-Earth object. This is something worth pointing out, that you don't discover an asteroid by taking a single picture and saying, there it is, I've now discovered it. It takes multiple observations over a long period of time to be able to measure where the object is and what its orbit is around the sun. And that's because we only have a two-dimensional view of the sky. We can measure an RA in a deck quite precisely nowadays. But the third dimension, that distance from the observer, and in particular both the distance and the velocity it has along the line of sight, are unknown. And so what you have to do is you have to watch the object as it moves, so that gives you an x and a y and a vx and a vy, and you have to wait for the velocity to change, for there to be an acceleration you can measure. And it's that acceleration that allows you to start to constrain that third axis, your along sight axis. And that's what allows you to go from the known position of the Earth to the position of the asteroid in 3D space, that acceleration parameter. And it's not a trivial conversion, because there is uncertainty. You have a PSF of your point, and so there's positional uncertainty. Accelerations tend to be small, even for near-Earth objects, so there is a fairly large uncertainty, and so you need to maintain monitoring of these objects for years, for multiple passes around the sun, ideally, before you can lock down an orbit and say, I know where this is going to be for the foreseeable future. This is even more compounded in the Kuiper Belt. The farther you go from the sun, the longer you have to wait to see deviations from a circle. Because the easiest thing to do is fit a circle to the object with no eccentricity, and then over time watch as it deviates from that. And so as you go farther from the sun, objects move slower, it takes a longer time. And so discovery becomes harder the farther you get from the sun. And so this is why, one of the reasons that we have fewer TNOs, not just are they fainter, but it's harder to discover them. But this gives us the orbit. That doesn't really tell us anything about the body itself. And so moving beyond orbits, what can we do? What information can we get from the ground or from spacecraft around orbiting the Earth about the properties of these objects? And the first thing we get is what we call, very unhelpfully, the absolute magnitude, the H magnitude. This has nothing to do with the H band. H was picked somewhat arbitrarily before the H band was defined, and that's why we have this V subscript. So we use H to represent an absolute magnitude for the asteroid. And so this is what the asteroid would appear, the brightness it would have, were at 1 AU from the sun, 1 AU from the Earth, and at 0 phase angle. So the opening angle between the sun to asteroid line and the asteroid to observer line would be 0. And if you think about that, it's kind of impossible. That requires the telescope to be situated on the surface of the sun, observing the asteroid. That doesn't happen very often for a number of reasons, mostly temperature and funding. But you can estimate that, right? Because once you have an orbit, Kepler's laws are great. Once you know the orbit of an object and you know the orbit of the Earth, you get distances and you get phase angles to very small uncertainties pretty quickly. And so by measuring an apparent magnitude, what I actually saw at the telescope, you can correct the apparent magnitudes here for distance, for the sun to asteroid distance, and for the asteroid to Earth distance, just 1 over r squared in both directions. And all that's left now is a phase correction. And so a lot of work has gone into modeling the behavior of asteroids over phase. Because an ideal sphere will have a cosine theta dependence. As the phase angle changes, as you're looking at like the phase of the moon, you'll see a crescent, and then you'll see a half, and then you'll see a gibbous, and then you'll see a full phase. And that has a pretty standard photometric distribution. Asteroids are not perfect spheres, and so their phase distribution changes. And so what you can do is by measuring your distance-corrected apparent magnitudes here, you can fit and find out what the magnitude should be at zero phase. And so this absolute magnitude becomes an initial marker for what the general photometric properties of the asteroids are. And it's a convolution of how big the asteroid is and how reflective it is. But it's our first piece of evidence we get once you start measuring astrometry, because you get photometry out of those measurements as well. Now, of course, it really depends on how accurate that photometry is. A lot of the surveys that discover asteroids don't use filters, or use very broad filters that are poorly calibrated. And so if you don't know what your spectral response of your detector is, it becomes difficult to then say what is the apparent brightness at a calibrated magnitude like the V-band. So this becomes complicated, and as new surveys such as Sloan Digital Sky Survey, Pan-STARRS, have started using actual filters that are actually calibrated, we're getting better photometric measurements. We're starting to get better fits to these behaviors. But already we can see for different kinds of asteroids, we see different photometric behavior. The letters here, so you're going to see a bunch of alphabet soup letters pop up. I'll get to how they were defined later, but these represent the taxonomic classes of asteroids that come from the colors and come from the spectra that we observe. The names were originally picked based on what we knew from the meteorite collection and wild guesses. And so the C complex here generally represents things that are thought to be carbon-rich for a rock in space. It doesn't necessarily mean it's goopy and covered in any sort of carbonaceous material, but there's more carbon mixed into the rock matrix than we get in other asteroids. M's we thought they were metallic. We flew by Lutetia and we saw a general rock. So there's something going on different there, but some of these M's should have metal-rich surfaces. S's are our standard silicates, or ordinary chondrite meteorites. They are the most well understood because they dominate our meteorite collection, and they're the things that are most like rocks on Earth. They're basically primarily silicate-based. V is for Vesta. Again, we talked about this yesterday, the largest body that partially differentiated, or almost fully differentiated, leaving behind a mantle. And so the rocks that come off of Vesta, the asteroids that come off Vesta, the best analog we have for them are basalts on Earth. They look like volcanic material left over on Earth because all the metal has melted, and you have actually gone through magmatic processes, unlike most of the asteroids. The E-class here was a guess at what we thought might be enstatite related. So we see these meteorites that tend to be very high albedo, that are bright. And so they said, okay, well, this might be an enstatite, so we'll call it an E. That doesn't necessarily mean there is a direct correlation. A lot of times it's a guess. But this also happens to be oriented in reflectivity. So C-type objects tend to be lower albedo. E's tend to be the highest. And so you see right away the behavior as a function of phase angle indicates how reflective the surface is. Dark surfaces tend to have this almost linear relation. Bright surfaces tend to be very flat with phase angle, but then have this sharp spike here. This is called the opposition effect. And so you can actually see it on Earth at times. So if you've ever gone hiking on top of a mountain and seen your shadow in a cloud below you, or if you're on a plane, you look out the window and the sun's behind you, you'll see a bright halo around the shadow of your head, or around the shadow of the plane. That's called a glory on Earth. It's a very similar effect where you get constructive interference of the light coming very close at very small phase angles. It constructively interferes and it becomes much brighter than you would expect from a linear relation. You get this boosting of light. And so we see this on asteroids because the surfaces don't have an atmosphere. And so you get these kind of strange behaviors, this photometric boosting. And we'll come back to the corollary of this plot in polarimetry in a little bit. So if we just take an object, we look at it as it changes its phase angle over days or months or years, you can build up this curve and you can say, all right, I'm starting to measure the photometric properties of the asteroid. But if you take those same photometric measurements and you look at it on a faster time scale, you can build up a light curve of the object. And so this is a very dense light curve of one object, 214 Ashira. And you can see this covers from 2004, September 2nd, all the way through October 20th, every few days. And by measuring photometry over a long period of time with very high precision photometry at a rapid cadence, you get to build up a behavior of the object as it rotates. And so if you assume an asteroid is basically a triaxial ellipsoid or a potato, and you spin it, then you're going to anticipate a bright, fainter, bright, fainter. So you should have 2 peaks and 2 troughs in your light curve for one rotation. And so in general, we see this for most objects. You see a peak here and here, and a trough here and here, in a roughly sinusoidal or sine squared behavior. But as you get more detailed measurements, you start to see changes in behavior. You see this little flattening here. The bottom, these are not symmetric, these troughs. These 2 troughs are not exactly the same, and this can be used to trace the actual physical structure of the object. It's deviation from a basic triaxial ellipsoid, from an ideal, into a real shape that we get for real objects. So one of the things you get from light curves is the first thing you get, hopefully if you've taken enough data, is the period and the amplitude. Your first question is how fast is the asteroid spinning, and how much does the magnitude change over that period? And so this is an object that we saw with WISE, and so it happened to follow us around for quite a while, and so we're able to get an amplitude of nearly 2 magnitudes. So remember, magnitude is a factor of 2.5 in flux, so you're talking about a factor of 5 in flux right here. So the axial ratio of this object has to be fairly significant. So it's either a very elongated body or a binary body, probably. We're also getting a period of around 10 hours for this one. And so we've seen everything, objects with periods down to 30 seconds, objects with periods of hundreds of hours. And there are systematics that prevent us from detecting things on both ends of that. For example, if you have a period of 10 hours here, that's about the extent you could ever get from the ground in a single night, just because the sun rises. And so you can no longer get sensitivity. And so if you have to come back the second night, you have this gap of 12 hours where you don't have data. And so you don't know how many times, what the behavior was when you weren't looking at it. This was an interesting case for the asteroid Itokawa. So Japan's first spacecraft mission that visited it, Hayabusa, went to go visit Itokawa, and they were attempting to measure the properties of the object from the ground before it got there. And this is work that Dave Tholen from the University of Hawaii was leading. He was having a terrible time trying to get the light curve properties of this object, and it turned out when the spacecraft got there, it was because the period of this object was 12 point small hours. And so every time he looked at it, it was showing the exact same face over and over and over again over the period of the months he was staring at it. And so we were only able to characterize half of the object. So the first thing we ask for is what's the period, what's the amplitude? Amplitude gives us shape. Period tells us how fast it's spinning, and that can be used to start to look at what sort of things have happened to it over time. Have there been collisions that have sped it up? Is it rotating so slowly that you wouldn't expect something that had been hit by small meteoroids over the history of the solar system to be rotating slowly? Because all asteroids should be rotating. We don't expect any objects with zero rotation. As you form the solar system, you have a disk moving around the sun. If you just hold an object fixed in that disk, it will still have some rotation as it goes around the sun, even if it's just the 1 year for whatever that object's year is. It will have a small initial rotation. As material accumulates, your angular momentum will build up, and so you expect to find objects with rotation periods. Something not rotating is entirely unexpected, just from basic physics. It's hard to hold things still. What we can also do is, if you have dense enough data again, you can start to detect binarity. And so this is something that Peter Pravik published in 2006. This object here, if you just look at the initial light curve, looks strange. Something weird is going on here. There are peaks that seem to be similar, and there's troughs, peaks and troughs that seem to be similar, but it doesn't really line up very well until you do a multiple Fourier analysis. So we usually anticipate an object to be spinning one time. So you have one period that the object is rotating over, and if you do a Fourier analysis of the light curve, you should recover that primary period in your Fourier analysis. However, when you look at objects like this, you actually get two periods out. So in this case, there's a 14-hour period and a 2.5-hour period. And this indicates a situation where we have an asteroid that's a binary. The 14-hour period, so that's this one here, so this is wrapped to a 14-hour period, is the secondary around the primary. The 2-hour period, so if you then subtract this fit, and you basically can recover now your 2-hour period, this is the rotation of the primary. And so you have a case where you have two different bodies, one that's spinning at 2.5 hours and a rather large moon, and you can tell it's rather large because the magnitude drops when it crosses in front of the asteroid are around half a magnitude. A rather large moon going around at around 15 hours. And you can imagine if this moon was also rotating and was non-spherical, that you would then get a third period potentially. Now for most of these asteroids, when they're in binaries, the moons are often locked. You get tidal locking. The objects are small enough and they're close enough to the primary that as they go around, they quickly dampen out, and you'll get a single period, which is the 14-hour period is both the orbit of the secondary and its rotation around the center of mass, around its own center of mass. But as you get more data and as you get better precision, you start to see strange behavior. So there have been reported asteroids, binaries, where you can actually see libration in the secondary in the light curve data alone. So never having visited this object, never having seen anything but the way its light changes with time, you can already determine that this is a binary asteroid. The secondary is librating, but generally locked to the primary, and the primary is rotating in some fashion. And so light curves are a powerful tool for determining properties of objects. However, they're incredibly expensive in terms of telescope time to obtain. You can see that this was, again, recovered over 3 or 4 nights in a single lunation. And you have to wait till the object is very bright. You have to use a big enough telescope to get very high signal-to-noise photometry. You have to do very short integrations. And it takes a lot of time. You have to basically spend the entire night or multiple nights on a single object. And so our light curve database is growing. The number of objects we have good light curves for is growing, but it takes a lot of time to get these dense light curves. Now, as you start to get more dense light curves, you start to get strange things like this. And so this object here doesn't show any sort of repetition. You can clearly tell it's changing. There's a huge, 1 magnitude light curve variation here. So it's changing, but over the course of a couple nights, it doesn't appear to be repeating. There doesn't seem to be any, and you could almost say that, yes, it's almost repeating here, but there seems to be a phase drift. Again, there's some correlation here. And then when you do the Fourier analysis of this kind of object, you get 2 periods of 2.8 and 6.7 hours. This object is tumbling. And so you can actually get an object where you don't have rotation around the principal axis, but you have it spinning and precessing at the same time. And so the axis of rotation is actually precessing as you're watching it. And this can indicate an excited rotation state, something that had an impact on it relatively recently in its history that has added energy. Because we don't expect things like this to exist for the age of the solar system. Tumbling rotation at fast speeds isn't the most energy efficient configuration. If you try and throw a pen up in the air and spin it, it will drop into a primary axis rotation after a while because the internal stresses dampen out any sort of non-principal axis rotation. And so for fast spinners, we expect them to get damped out. And so this can indicate a history of recent impact that spun it up and added angular momentum to the system that was not anticipated. We've also seen tumbling asteroids that are very, very long period. And so things that rotate around their axis once every 300 hours. And in this case, there's just so little angular momentum in the system that the pole isn't strongly fixed, and it's not necessarily just precessing, but it's just wandering because there's so little angular momentum in the whole system. And again, how we get objects that are rotating that slowly is difficult. You can imagine that something hitting a nice triaxial ellipsoid can cause it to spin and wander around in a chaotic, tumbling fashion. But how do you hit something the right way to almost stop it perfectly? That's very convenient. And so it's not likely to be an impact-generated event, but very slow tumbling is probably due to a different mechanism called YORP. And I'll get to that more on Thursday when I talk about the Yarkovsky effect in detail. But this is a way of sunlight, solar pressure from sunlight and from thermal radiation slowing asteroids down and changing both their orbits and their rotation rates. So this is our tumbling asteroid, the two periods. If you then take a double sinusoid and plot the data over that, you'll see that it fits a whole lot better. And so when you do this Fourier analysis of these objects, you do get much better fits. There's still some deviations. It's not perfect. And so two simple sinusoids often aren't enough. And again, that's partly because of the shape of the object itself. That asteroids aren't triaxial ellipsoids. They have craters, they have divots, they have pieces taken out of them. They're non-ellipsoidal. And that causes different behavior than we would expect from a simple sinusoid. So on the other end, we can look at superfast rotation. So I said that we have objects that rotate very slowly. We also have objects that are spinning quickly, and I hope you can see this in the back, but if you plot up all the periods we know for asteroids against their diameter, you see a cloud of objects down here, and what looks to be a fairly strong cutoff right here. And so as you get more and more objects, it became apparent that at sizes larger than a kilometer, almost nothing was rotating faster than 2 hours. And in fact, it was nothing until around 2002, 2001, when the first object was discovered. But until that point, there were no big things rotating quickly. And so the interpretation of this is that these objects aren't rocks. They're not monoliths. They're not single entities. They're a pile of rubble. And as you spin a pile of rubble up faster and faster, gravity is no longer sufficient to hold it together. And for densities that we expect asteroids to have, of around 2.5 grams per cubic centimeter, 3 grams per cubic centimeter, if you do the math, you get that a period of around 2.2 hours is where they're expected to dissociate, to break up. And so this was taken as strong evidence that pretty much every asteroid larger than a kilometer in size was a rubble pile that had internal fractures. If it wasn't necessarily just a pile of gravel, but it had enough internal fracturing from its history of impacts in the solar system that it could not self-sustain, it couldn't hold itself together as it spun faster. We did see very small objects up here rotating at very fast rates. Again, I said I think the fastest on record right now is 26 seconds or something, a small near-Earth object spinning incredibly rapidly. And you say, okay, well, you have these things that are spinning super fast, and we'll say that those are single rocks. And you can spin it arbitrarily fast before it bursts itself apart. And we expect here, this dashed line is kind of, okay, well, if you do a general strength behavior of how objects are supposed to hold together over time as they, how the strength of an object scales with size, then you would expect this kind of behavior where small objects, big objects are gravel piles and can't hold themselves together, and as you get smaller, you get stronger and stronger. And so anything under this curve should be allowed. But still, we're starting to get objects that are even exceeding that expectation. So we're starting to see large objects here that are above even what you would anticipate in a generous strength-dominated regime. And so this implies that you can get fragments, you can get kilometer-scale objects that are single rocks that haven't been shattered from previous impacts, that aren't reaccumulations. And so how you form something that big is one of the outstanding problems. But it's one of the things you get by doing enough light curve surveys. You see there's thousands of objects down here, and you start to get handfuls of points in this super fast regime. And so this has been one of the payouts of a lot of the light curve surveys that have occurred. One of the other really interesting ones, so if you take a light curve, and I do a single light curve period, I can get a period in amplitude. But if I come back a few months later, when the object is at a different aspect with respect to the Earth, you might see it rotating in a different fashion. I see it another year later, and you see it rotating in yet another fashion. And so the period should be the same. You don't expect how fast it spins to change. But the amplitudes will be different based on your viewing geometry. For instance, if you're looking right down the pole, you would see 0 amplitude. You would see no change in the brightness. If you're looking at the equator, you'd see a maximum change in brightness. And so if you get multiple apparitions of these, you can build a 3D model. And so Joseph Durich has been leading a lot of work on this with his DAMIT database, that I forget what that stands for, it's 3D asteroid models based on both dense and sparse Likert photometry. So a lot of Likers I've shown so far are dense. You take an observation every 30 seconds for a night, and you build up a very nice light curve. But a lot of our surveys don't give us that. They might give us a couple of observations a night, and then a couple more the next night. And to first order, you don't get a lot. From a single night of data, it doesn't give you a lot of information. But if you have 4 observations every night for years, at various changing aspects, you can start to build up, from this sparse photometry, 3D models. And so this is one of the 3D models that he's able to produce, he and his team are able to produce, of an example asteroid here, 130 Electra. And so as you watch these things rotating over long periods of time, you start to see features. You can see that it's not, there's divots here, and there's ridges here. Now, a lot of these models make an assumption that the object is completely convex, that there are no concavities, because it becomes very difficult from light curves alone to say, is this a crater or is this a flat plate? They have basically the same photometric behavior. And so these initial models are like a shrink-wrapped version of the asteroid, where there could be craters hiding under the surface. But new models are being developed right now that can take into account crater. They again require much more data, because you need to have very convenient viewing geometries where you get light coming right down the crater in one instance. But you can now start to get 3D models of asteroids just from the photometry alone. And all of this I've been talking about so far can be single band. You only need to do observations in one band, and as long as your photometric 0 point is known each night and you can offset it correctly, you're good. But what happens if you have multiple bands? And this is where colors start to come in. So people have been doing color work for a long time on asteroids, but in 2001, Ivzich's 2001 paper and Parker's 2008 paper, they published the Sloan colors for a large number of asteroids. And this is where we really stepped up an order of magnitude in terms of our knowledge of colors of asteroids. And so they define this A star parameter, which is a combination of the G, R, and I bands, and then the I minus Z color of asteroids. If you plot up all of the known objects, you see this interesting behavior where you have a bimodal distribution here and a tail heading down there. And so when this group put those same objects with these colors, and these basically coloring the points based on where they fell on this diagram, onto the semi-major axis and inclination plot, they're able to show that you recover the asteroid families again. That you see the same compositional gradient I showed you in Albedo. Now this was a few years before we had our Albedo data, so this was some of the first evidence that families in general really were compositionally homogeneous. And more to the point, so you see this, okay, this clump here is the colors we expect for these carbon-rich objects. This clump here is the colors we expect for silicate-rich, and down here are the V-types. And so the objects that are members of the Vesta family, because of their unique history, show up uniquely at the location of the family in the main belt. So what this tells us is that color is a great way of determining some of the spectral properties of objects. But conversely, we don't see V-type objects in much of the rest of the belt. We don't see any other large families. We see a couple of them here and there, but we don't see any major objects that you would expect should you have had 100 Vestas in the main belt that were broken open, scattering their mantle material around and sending their cores into Earth so that we can pick up the iron meteorites on the ground. And so this is what's referred to as the missing mantle problem, that you have iron cores from effectively 100 objects and mantle material from just one. And we don't know how you make a core without making a mantle too, so where did this mantle material go? Good? Okay. With the colors alone, you can start to do taxonomy. And so this is work Carvano published in 2010, taking those same Sloan colors now and doing your basic taxonomy. So you see that your D-type objects here tend to be very red. You have a variety of behaviors, in particular this downturn here at around 1 micron. And the farther you get into more silicate-rich, more heavily processed, the deeper this tends to be. And so this 1 micron band, and we'll go back to this later when we get to spectra, is an indicator of olivine and pyroxene in silicates. So it shows evolution of the silicates in some amount of heat. And so the deeper this downturn showed up, the more, in particular, olivine you expect to find in the object. And so this is why this I minus Z color here, which this is I and that's Z, that's why it was so diagnostic of the V-type objects here, is that in general everything else is pretty flat, and the V's show a very much stronger I minus Z color. So this is with 5-color optical survey. You can also look at what do the colors tell us when you go into the near-infrared. So the 1 and 2 micron range, the J, H, and K, or J, K, and Y in this case, it's not quite as clear-cut and dichotomous. You don't have this very significant spread between the C's and the S's that you saw in our previous work. There is a dividing line here, but it doesn't show up as clearly. But again, you see the V-type objects get pulled off in this direction significantly. This is again because these filters tend to fall right around where you expect silicate absorption bands to fall. And otherwise, you can take objects with known classifications, figure out where they fall on this plot of JK minus Y minus J versus Y minus J, and then take all the objects that you have no classification for and map them back. And so from near-infrared colors, you can start classifying objects that didn't have spectral classifications. Taking this further, this was earlier work, but on a smaller set, Zellner et al. In 1985 did an 8-color asteroid survey. And so this is where a lot of the letters that we use come from. This is one of the first ones to try and assign letters to these things. And so you have the B asteroids because their slopes were a little blue. You have the C's because they look like boron carbon. You have your S types here because they look like they're silicates. Our A types, again, there's only 4 of them, but they tended to have high olivine content. And when this work was done, they had 3 different classes of objects that all had identical spectra. These E's, the M's, and the P's. The only way to distinguish them, they're otherwise pretty much boring, very lightly red spectra that are distinguished only by their albedo. In the 80s, they had a few albedos from IRAS. And so you're able to, about 2,000 objects had measured diameters and albedos. And so they're able to distinguish this EMP classification. All the future surveys didn't have that until the WISE albedos were published, and so wound up calling this the X complex. And so it was kind of a conglomeration of asteroid taxonomies. But you have to remember that this is 3 very distinct mineralogies that just happen to look the same. And so while spectra give us a lot of information, you can see that this is not like our AGN spectra that we saw earlier, or stellar spectra. You don't have significant gas lines. You don't have just any sort of broad absorption lines from ionized gases or anything. This is geologic spectra. And so minerals in rocks don't behave very nicely. Absorption bands are incredibly broad, many microns across in some cases, and not very fine-grained. And so you only get a finite amount of information from these spectra. And so they're a lot harder to interpret than stars, which give you their composition pretty much off the bat with a high enough resolution spectrum. But if we do take an optical spectrum of an asteroid, we get something like this. And this is not a great spectrum, but it's one I had handy from Palomar data that I took a few years ago. And this is just a 2-channel optical spectrograph. So a blue and a red end, and this probably should match up, but I didn't do the data reduction perfectly. But most optical spectra tend to run from around 400 nanometers to 900 nanometers, about 0.4 microns to 0.9 microns. If we go back real quick, I want to point out the ECAS survey you'll see had 2 points short of 400 microns. This is because the 8-color asteroid survey wasn't using CCD detectors. It was using photodiode detectors. And an interesting feature of photodiodes is they are very blue sensitive. They were really good at detecting light in these wavelengths. And you can see that some of these objects have unique behavior. The F-type here has a different behavior than the B's. at this very short, like near ultraviolet wavelengths. CCDs no longer detect this regime very well. They've been designed for optical and near-infrared, and we don't really have very good UV detection anymore. And so a lot of our spectra we cut off at 400 meters because the sun's getting faint, you're not getting a lot of photons to the asteroid, so you don't get a lot of photons back to your telescope, and then your detector doesn't detect many of them either. But we are missing a key part of the spectrum in these objects. And there isn't really a good solution in the near-term horizon. And this is not just being faced by asteroid people. The UV galaxy people have their own sets of worries about this. But it's just something to keep in mind that UV is something that we're forgetting, that we haven't really done in a while in the optical for asteroid work, and there is information there that we're losing. So if you take an optical spectrum and you take spectra of hundreds of objects, like Bobby Buss did for his thesis, you can build up this interesting scatter plot of behavior of objects across the optical wavelength. So this is still the 0.4 to 0.9 microns. And this is roughly sorted in the way that the principal component analysis they did of these spectra sorted them. And so this is basically principal component 1 and 2 space. And you can see that in the optical, the diagnostic features are how steep is this slope and how sharp is that drop on the back end. And so the D-types here show very steep, very red slopes. They're some of the reddest objects in the solar system. And the V-types are also pretty red up until you get to that 1 micron absorption where they drop off rapidly. And so this dichotomy here of increasing steepness and then increasing 1 micron absorption allows us to break up objects into various categories. And you can see we went from about 10 different categories in the ECAST survey to now we have something like 20 here, and some with various subscripts. And the deviations between these are subtle and sometimes indicate mineralogy. The depth of this 1 micron absorption can really inform the different kinds of olivine that formed on the surface.
Are these spectra averaged over several rotations, or do you expect the composition to be homogeneous across the surface?
They typically were not, well, typically these spectra are taken over a period of a couple hours. And so if you don't know the rotation period of the object, you just assume that it's homogeneous across the surface. There have been surveys looking for compositional changes in spectra across the surface. Really, the only conclusive thing we found so far is Vesta. Vesta shows significant changes in its spectra across the surface. There are subtle changes seen in a few other objects, but they're very difficult from the ground to disentangle from atmospheric effects and instrumentation changing effects. So, because there's not a lot to work with here. And so oftentimes it's just a subtle shift in slope. And is that shift in slope because the minerals changed or because a thin layer of cirrus passed over? But Vesta was a absolute certainty that it's changing, that changed across the surface. Everything else is assumed to be homogeneous until proven otherwise. And it's, in general, a good assumption to first order. So once you have optical spectra, if you extend your wavelength coverage into the near-infrared, now you start to get a better handle of both the behavior of the slope at longer wavelengths, but also the 1 and 2 micron absorption features. And again, not a great spectrum, just what I happen to have handy. But what you can do is start from the peak here, where this depression begins, and where it ends. Do the same thing for the 2 micron band. And if you integrate this area, you can start to look at the band area ratio. How deep the 1 micron band is compared with the 2 micron band, what the ratio of the areas are, and where those band centers are. And this, you can do this for a large number of asteroids. You can also do it for a large number of meteorites, and then compare the results. And so you can start to use this to constrain for objects that show these 2 absorption features what the mineral composition of the objects are. And so this is how we start getting, olivine to pyroxene ratios for a large number of asteroids. And so this is work that Francesca DeMaio, she basically continued Bobby Buss's work into the near-infrared for her thesis. And so this is that same, 0.4 to 2.5 micron chart. And so if you actually look at this spectrum here, we kind of get a bump and two small wiggles, and that looks a whole lot like this K-type spectrum here. And so that near-Earth object is probably a K-type based on those spectra. But you can see that for like this class of objects, you have some information. You have this broad 1 micron region that is typically olivine based, and this 2 micron region that is a pyroxene based feature. And so you would expect for, the V types have a strong olivine and a strong pyroxene. This A type here is an asteroid that looks to be almost entirely olivine. No other silicates, no other pyroxenes, and so you get this very significant olivine depression with no 2 micron feature. And so for the silicate-based objects, you can start to do mineralogy. For these objects, we can do very little. The solar system hasn't given us a lot, but a short word of 2 microns or so. We don't see significant absorption from any of the silicate materials. We don't see olivine. We don't see the pyroxene. And part of this is because when you sprinkle a small amount of carbon onto the surface, it absorbs everything. And so all of your absorption bands just go away. But we can see some features out at 3 microns. These data are very, very hard to obtain because you have to wait till the objects are close to us usually. You have to wait till they're close to the sun, and so they're not just reflecting light, but emitting light, so you have to correct for the thermal emission that's anticipated. And then you also have a bunch of water in the atmosphere, and that really swamps this whole region. So you have to have objects that are very bright. So the survey of 3 micron spectra is only of order of around a dozen objects, a couple dozen objects. And Dries Takir has done a lot of this work for his thesis. But if you can do this kind of regression line across the band, you can now measure this 3 micron band depth and the position of the maximum depth of that 3 micron band and correlate that with water content in the silicate matrix. Because this band correlates with phyllosilicates. And if you haven't taken much geology, phyllosilicates are kinds of clay. Basically, they're these thin layers of silicate with layers of single atomic layers of water in between. On Earth, they form in regions where you have liquid water at the time that the rock is being deposited and is forming. How do you make a phyllosilicate on an asteroid? Unless you have liquid water somewhere below the surface. And so this is indicating that there's a history of warmth, and this might be from the aluminum-26 melting any ice that was initially within the rock, that was there long enough that silicates were able to form around semi-liquid water. And so we're starting to see these features of a strange history in our solar system of these dark objects that show us nothing else, right? Because short of 2, these are just flat, dark slopes, slightly red. But once you can get up to 3 microns, that's where a lot of the really interesting information comes from. And so this is one of the exciting things that telescopes like James Webb will be able to help with. If you can take 3 micron spectra of asteroids, where you don't have this atmospheric water band knocking out a lot of your data, you can start to really do a survey of how liquid water was distributed early on in the solar system. So, all right, so that's the end of spectra. Any questions on spectra before I move on? I know that's a lot of spectra talk. Okay, if you have more, we can come back. Because this one's my personal favorite, polarimetry. Everyone doesn't like polarimetry because it involves vectors, and vectors are hard or something. But polarimetry is basically how the vectors of light change as it reflects off the surface. Remember, we had our opposition effect that we saw in photometry because we have constructive interference with the light at very small phase angles. And that works because asteroids are atmosphereless. They don't have an atmosphere to scramble light, and so you can get strange behaviors. The other strange behavior you get is changes in the polarimetric properties of asteroids as a function of phase angle. Now, I'm sure most of you are familiar with polarization of scattered light. If you're driving down the road and it's wet, there's light will be polarized perpendicular to the scattering plane. And this is why polarized sunglasses do a great job of reducing glare when you're driving or reducing glare if you're boating. Because there's a strong polarization component that happens at around 90 degrees phase angles. So the angle between the incident and emitted ray, when it's around 90 degrees, you get this maximization of polarization. But for asteroid surfaces, as you get down below phase angles of 20 degrees, the sense of polarization of light flips. And this is due to some weird effects with destructive interference of the light as it goes into the matrix of the material, bounces off two different surfaces and comes out. And if you do ray tracing of both paths, there's a slight path difference as a function of phase angle that causes the polarization sense to flip. And so again, if you look at these different classes of objects, you see a different polarimetric behavior. These high albedo objects have very little polarization as a function of phase. And surprisingly, the objects that reflect the least light are the most likely to polarize it. And so you can look at how deep, and so this is percent of polarization. So we're only talking here of polarizations of 1 or 2% of the light. It becomes very tricky to measure this because it's a very small fraction of the total photons. And so if you want to measure light to basically 0.1% polarization, with that kind of accuracy, you need to be collecting over 1 million photons per image for your object. And so if you do the back of the envelope, that requires you to have a very bright source with a very big telescope and to understand your systematics really well. And so this is why we don't have a ton of polarimetric data, but new instruments are being put online that hopefully should be solving a lot of these problems. So if you look at the depth of polarization here and the slope of this curve as it crosses through this 0 point line, both of those have a relation with the albedo. And so if we compare this slope of the polarization or the depth of the minimum polarization and compare that to our albedos, we see that, yeah, you do see a correlation here. And so from our polarimetry alone, we can get an independent test of how reflective the surface is, just by the way it changes the vectors of light as they're reflecting off of the object. So yeah, this one is, I like it a lot, but it's very obscure and no one really does it. But it's fun. But a lot of these things, so I've talked about, how polarimetry I showed against albedo and showed there's a correlation. One of the best ways to get albedo is to use thermal infrared data to get the size of your object. Remember I said the brightness you observe with an optical telescope, with this absolute magnitude, when you make that correction, it's a conflation of how big the object is and how much light it reflects. So if you have an independent way of measuring how big an asteroid is, then you can quite easily calculate how reflective it is. And so my favorite way of getting asteroid diameter is from the thermal infrared. And the reason for that is shown in this plot. Can you spot the asteroid in this image? Which one's the asteroid? It's the bright red one in the middle of the image. All the stars are blue. So in thermal infrared, asteroids are the brightest things in the sky. At 10 microns, these dominate what we detect because the spectral energy distribution is falling off for stars. These things are super bright in the optical. They're putting all their energy out in the optical.
You mean ground-based observation or space?
So this is from the NEOWISE satellite, or when it was cryogenic from space.
Atmosphere.
Yeah, because if you try and do thermal infrared from the ground, it's like building a telescope out of light bulbs. Because your telescope is glowing, the air is glowing, it's very difficult. So there is some thermal infrared done from the ground, but it is far, far easier to do from space. And so this is why WISE was so successful. This is why they're launching James Webb and spending, what is it, $8 billion now to launch it or something? Because space is the place to be cold and to avoid all the heat that you would get from the Earth and the atmosphere. And so, again, the way we do this is you can measure the thermal emission from asteroids, and it becomes this rather simple equation of if your sun is here, once you have an orbit, you know this r-sun distance, and you know this d-Earth distance, and you know this phase at any given time. You can calculate it down to effectively infinite precision for as far as our case is concerned. And so if you know, if you have a flux measurement here, then the only real remaining variable is how big the object is. with the hand wave of I have to know how heat is distributed across the surface of this sphere and whether or not the asteroid's a sphere. But taking a simple asteroid thermal model, knowing all the rest of the parameters, you measure a flux, you get a diameter. And so this is why WISE was so successful. I'll talk more on Friday about some of the other results that we've had with WISE and why it was such a useful machine for this. But once you have this data in hand, then if we go look at our reflected light, it's the same setup. Right? We still have the light, we still know the R sum, we still know the D Earth, we still know the phase. We get the diameter from our infrared, and now only thing left is albedo. Is this bright white like chalk? Is it dark like coal? And so by measuring these two things independently, that's what you can get. I should clarify, in solar system we talk about albedo a lot, and it's not necessarily intuitive. We don't talk about albedo and mean bond albedo. So in general, the capital A albedo here is what you learned in basic physics of, the amount of flux reflected over the amount of flux input. That's the general albedo. This is the bond albedo covered over 4 pi steradian integrated sphere. What we tend to talk about is this PV term, this geometric albedo and in the V band. And so this is a reflectance of the real object as compared to what you would expect an ideal reflector. So an ideal Lambertian disk, how much light would it reflect back at zero phase? This is more similar to, I find that the geometric albedo is more what you would intuitively expect from seeing a rock, looking at the fraction of light bouncing off of it. But it does have the funny caveat here of you can get geometric albedos above 1, above 100%. And so we don't see this in many places in the solar system, but icy moons of Saturn, like Enceladus, things that have very, very high reflectivities, can reflect more light than you'd expect from an ideal reflector, just because they scatter it straight back. So let's clarify albedo. So I said we have, with a thermal model, we need to have a basic idea of how temperature is distributed across the surface of the asteroids. And so these are the two equations that set up this thermal model that were set out by Alan Harris, who until recently was working in Germany at DLR, for what he called the NearEarth asteroid thermal model, which has been incredibly useful for things that aren't NearEarth asteroids as well. So all it says is that you have a T max here that's distributed as cosine to the quarter power for this omega is angle from subsolar point around the body. And this T max is just 1 minus your bond albedo times the solar flux. And so this is you're calculating your T subsolar that you would do in a standard physics equation, just with an added parameter here, this eta, which he called a beaming parameter, and is effectively a fudge factor. It's a knob you can turn to correct for things we don't know about our model. So how non-spherical is our asteroid? How non-ideal does it behave? And in particular, if you look at this model here, this temperature distribution, it gives you a distribution from the subsolar point to the horizon of where the sun sees, but on the night side of the asteroid, it assumes the temperature is 0 Kelvin. And so there is 0 flux contributed from the night side of the asteroid. So for objects that are in the main belt, for instance, which are far from the Earth, you only see them at phase angles of 20 degrees or so, or less. There is very little night side to worry about. As you get objects that are actually near Earth objects, where you can see them at quarter phase or more, the assumption that there is 0 flux on the night side starts to break down pretty rapidly. And so some of that can be corrected by just tuning this eta knob and fixing your parameter that way. However, in order to tune that knob, you have to have 2 different measurements at thermal wavelengths. Oh, that's not a question. Okay. And so having 2 independent thermal measurements allows you to basically modify this model to behave in a way that corrects for this lack of night side emission. But we had that with Y's, and so we were able to get this plot. And so this is showing diameter of asteroids time and against the geometric albedo. And I just picked this color coding for across the log albedo for future plots. But what we see is very clearly two distinct peaks in albedo space. This is tracing back to these two compositions. We see the silicate-like objects up here, the carbon-rich objects down here. And what we don't see is any change in these peaks as a function of size. So what this says is that dark objects are made of the same stuff regardless of size, and bright objects are generally made of the same stuff regardless of size. We don't see any sort of turn-up that, for instance, if objects got darker over time due to space weathering, which the moon definitely does. We've seen on lunar rocks a darkening of the surface. You would imagine small objects might be newer, recently broken up, and so might be fresher. We don't see any change, at least down to the sizes we're sensitive to, of around a couple kilometers, of this picking up at all. If we take a look at these albedos now and just do a histogram for the various parts of the main belt, outer main belt here shows again, we don't see any real change in the centroid of these distributions. So dark objects in the inner main belt look to be have the same albedo distribution as dark objects in the inner main belt. There are more of them in the outer main belt, but they seem to be the same stuff, which might not necessarily be true in the inner main belt, for the S-type objects rather, where you do see this peak shifting over from here to here to here, possibly tracing a gradient in these silicate objects. And so this is one of the things that we say, okay, maybe these dark objects were implanted from some icy population and put in to the inner main belt, and maybe this gradient here traces our composition differences. One of the other benefits we got from WISE, and I'll talk about this more on Friday, is near-infrared albedos. So we observed at 4 bands, and for a few thousand objects, we got reflectivity at 3.4 microns. And we see now 3 populations. Of course, we have this effect here. This is an incompleteness, because if W1 is a reflected band now, objects are more easy to detect at optical wavelengths, basically at infrared wavelengths rather, thermal emission, than they are in reflection. So you have a loss of small objects that have low albedos because they're harder to see as they get farther away than they are close. But what we see is this distinct breakup of 3 different populations. So we can use the albedo as a first-order spectral check for the different kinds of populations in the belt. We can also do more detailed thermophysical modeling. So I said, okay, if we take Needham, which is just a simple toy model, and you assume a temperature distribution, you have this knob you can turn eta, you can get a size from that. But if you have an object that you've seen at many different times, at many different viewing geometries, much like we did with the light curves, you can discard that assumption that you need to have a simple model that has no night side emission. And so you can build a model that has a parameter that you can fit now, that's the thermal inertia of the surface. You can actually look at how is temperature distributed around the surface. The problem with these models is there's more variables, so you need more data to input. And they take a long time to process because you actually now have to trace how the surface talks to each other thermally and how features on the surface, if you basically have light shining on it, the amount of light that, for instance, if you have a crater, warms up one side of the crater and the crater heats a shadowed part that you then see. And so because you require more detailed simulations, these models take longer to run. A simple Needham model will run in a few seconds. A thermophysical model with 5 epochs of data will run in 2 days or so. And so it's computationally more intensive and requires more data, so we can't do it for everything. But for the few objects we can do it, now we can simultaneously fit the diameter at a bunch of different epochs, as well as the other thermal properties, and get a much better fit. And so this is just for the NearEarth object Phaethon. This was 5 epochs of data that we got for it with NeoEyes, including one that was in the 4-band phase and 4 that were in the 2-band phase. And this allows us to put stronger constraints on our diameter than we would be able to with Needham alone. So, okay, any questions on thermal infrared before I move on? No? Okay, good. It's late. I was tired. So the next topic I want to cover real quick is asteroid radar. And this is really cool because this is the only time where instead of waiting for the sun to shine on something and looking at reflected light, we actually take a giant radio dish and we scream into the void with it, and we bounce radar signals off of the asteroid and recover them. And so this gives us, foremost, very accurate astrometry. Because remember, in those initial images, we can look at an asteroid moving with time, and we get an XY position, XY velocity. This gives us exactly how far away it is, because if you know when you sent the radio pulse and when it came back, you now know, because of the speed of light, exactly how far that asteroid is from you, and based on the Doppler shift of the frequency, exactly how fast it's receding or coming towards you. So combined with astrometry, radar can provide amazing constraints on orbits in a very short amount of time. But we can also get physical properties from it. And so how long that signal takes to return can give you how big the object is, because the leading edge of the asteroid as it faces you will reflect radar first, and then as the wave goes around the sphere, you'll get later and later reflections. And so if you build that up, you can turn this time delay into a 3D model. And in addition, because asteroids are rotating, the radar reflections from this side will be slightly blue shifted, and from this side will be slightly red shifted. And so now you have a 3D model that's built up of objects because of their spinning and because of the time delay. You get a full model of this. And if you watch it over a full rotation, you can see the whole object. Now, there are some problems where you can't tell if something's the north or the south from an initial image, because the time delays will be the same for them, and the Doppler shifts will be the same. But if you have multiple observations of an object at different viewing geometries, you can start to break the degeneracies between north and south, and they can result in a 3D model, in this case of Bennu. So this is the asteroid. This was published a few years before OSIRIS-REx got there. And you see that same top shape that we saw when we got there. And in fact, the size returned from this model and the shape returned from this model matched to within a couple percent of what the spacecraft saw when it got there. And so with a lot of radar data, you can get very good models of the shapes of these things. You can also find binaries. So this is a series of plots, different times. So what we're seeing here is you can imagine that the radio telescope's at the top of the page, and it's sending the radar light down. And so this is different time delays, effectively. And so this is the first surface that responded. This is the last surface that responded. And left to right, we have Doppler broadening. But if you just plot up time delay versus Doppler broadening, you get what looks like a pretty nice image of an asteroid. And what they saw here in this object is this little speck of light was a binary. It's a secondary object, and you can see it going around it. The Doppler shift is small, and the time delay is small, but you can get a size for it, and you can get an orbit for it as well. And what's really nice about binaries is if you have an orbit, you know the mass of the primary. And so from a single set of radar data, you can get masses for these primary objects, and you get the size of the primary, so you get density as well. And so this is one of a great way of de-encoding the mass, which is incredibly hard to get from most objects. Here's another fun image. This is a contact binary. So this is bistatic observations, where the object is so close to the Earth that the radio telescope, normally what happens is the radio telescope will broadcast out, flip over to the receiver, wait for the pulse signal to come back, and then it will flip back, broadcast again, and so you'll build up this data over long periods of time that way. for some near-Earth objects, they're so close to the Earth that they physically can't switch the receiver and the broadcaster fast enough. And so what you have to do now is employ a second radio telescope, one of which is doing the screaming and one of which is doing the listening, and bounce it off this way. And what that gives you, though, is incredibly high-resolution data. And so, because the objects are super close and they're super bright, and so in this case you see an object that is either a contact binary or is something that's almost touching. Two objects of almost equal mass, almost touching, similar to what we saw for Itokawa and Totatis. One of the other really nice things that you get with radar, you know how much light you're putting out. And you know how much light you measure when you get back. So you can get an albedo. You can know how much the surface reflects, whether it's reflecting 50% of the light or 5% of the light. And as far as we can tell, this tends to be correlated with metal content. So this is a plot not of all objects with radar, but only of objects that have high radar albedos. But this is one indication that, these objects might actually be iron cores. Again, it's pointing back to our missing mantle problem of if we see these iron cores floating around in space, where is the stuff that was around them originally? And another one favorite of mine is occultations. So as asteroids move across the sky, every so often they'll move in front of an asteroid, in front of a star rather. And if you position telescopes along that line of the shadows moving, you can see it wink out at different times and build up a 3D model of your asteroid. And so this is another way of getting independent size measurements, totally distinct from anything else, all based on the motion of an asteroid. Until recently, the problem with this was that we didn't tend to know where the stars were or where the asteroids were well enough to predict where the shadow would fall to within 100 kilometers. And it becomes a pain in the butt to set up many stations over thousands of kilometers. It's just not feasible. Now with Gaia, we know where stars are really, really precisely. We have asteroid orbits really precisely. We're going to start to get more and more occultations, and so we should get more and more interesting discoveries. Occultations can give you binaries. This is 90 Antiope, and so you see two separate shadows here, and on that shadow you see a huge crater. A bite was taken out of that asteroid. Again, revealed by occultations. And I don't think I'm not introducing this to most of the people here, because the Observatoire National was one of the key players in finding the rings around Triklo. And so this centaur, the occultation data here show, in addition to the shadow you expect from the main body, two rings. Two very thin, very narrow rings around this object, otherwise unexpected. And this has become a huge problem because we have no idea how to make rings around this object. We were struggling trying to make rings around Saturn for long enough, even though they're there. Now, how do you make rings around an object that's in an unstable orbit and so has undergone gravitational perturbations? So, I don't know. This is cool. And most recently, we have direct imaging. Our telescopes are getting better. Our instruments are getting better. This is from Sphere on VLT. This is one of those 3D models based on light curves. This is a direct image. Our AO is getting good enough, we're able to actually get multiple pixels across our asteroids and start to see that, yes, the shapes do match. And there might even be features. You can start seeing craters on the surface of an asteroid from the surface of the Earth with our AO. And so as we get to bigger telescopes, to our 30-meter class telescopes, we're going to see more of this. And it's really going to be fascinating. So just to close quickly, a few other things. I've talked a lot about the stuff you can get besides orbits, but orbits do give us a few other things. One of the things they give us is mass. And so this is an incredibly boring table, but what it says is, for the asteroid series, you had a whole bunch of asteroids that passed relatively close to it. And if you know their orbits really well before and measure them really well after, the slight deviations in their orbits allow you to measure the mass for hundreds of objects. And as we get better and better astrometry in the future, again with Gaia, we're going to get masses for a large number of these objects just based on the way the orbits pull each other. And you can also get measurements of the Yarkovsky effect. So this is something, again, I'll talk about more on Thursday, but this is effectively solar photon pressure changing the orbit of the asteroid. And so if you see, the observations here are marked in this plane with the x's. And so here's the mean of where you observed it. Here was the sky motion. And so you expected it to fall in here, and instead it moved in there. And so you can see this shift here of where you thought the object should be and where the object was, just based on the way the photons affected the surface of the object. And this is all just based on astrometry, just very, very precise astrometry. So I'm almost out of time, so I will have one last topic, and this one's near and dear to my heart, is Oumuamua. And one of the cool things about all that I've told you is by categorizing and making taxonomic classes and doing all these measurements to try and constrain the physical properties of objects in our solar system, when we get a visitor that comes from outside the solar system, we can do the same things to try and see, does this look like the stuff in our solar system or not? And so this is the orbit of Oumuamua. It came in, it did a close pass by the sun, it came out, it actually went relatively close to the Earth, 0.2 AU, I believe, from the Earth, and then sped on out. It came from effectively the direction of local standard of rest, but because we have, it was the first interstellar object we found, a lot of telescope time was used, and we started finding stuff. We took a light curve, like we did with other asteroids, and what we found is that it was tumbling unexpectedly, that it had a very high light curve amplitude, and that the period wasn't necessarily, it wasn't on a simple principal axis period. It was doing some sort of strange tumbling motion. We took spectra of it, and it seemed to look a whole lot like our D-type asteroids, which we think are these dead comets, something that was icy and no longer is. And we saw Yarkovsky drift. So this, you can see here, this is the residuals in right ascension and declination for an orbit that doesn't include Yarkovsky. And these points here were the initial measurements, but it's these two out here that were, about a month after discovery that are of most interest. If you add in a non-gravitational force, you get a better fit to the data. And so this implies that something is going on. Either it was Yarkovsky, or it was cometary outgassing, or it was the thrusters on the alien spaceship, changing the direction on the way out. It's not aliens, though, but it looks like aliens, but it's not aliens. So in my next lecture, so this was kind of covering how we know what the physical properties are of these objects. On Thursday, I want to talk about asteroid families and the catastrophic collisions that make them, and the chaos in the solar system, and how we determine how old these families are, because it's the families that let us know what's been going on in the solar system over the last 1 billion or 2 billion years, in terms of massive collisions, in terms of grinding, in terms of evolution of orbits.